Welcome to Module 1, and in this module we're going to discuss a kind of problem that I refer to as order log n behavior. This is a kind of behavior that is extremely efficient, and after this module you'll understand why it's efficient, and hopefully you'll be able to use it in your own algorithms. You often find yourself faced with the task of determining whether a collection contains a certain element. It could be a list, it could be an array. In this module, I'm programming in Python, so these would be Python lists. And the Python language has a statement called in that allows you to quickly check to see if an element is in a list. What could be simpler? Now, normally you don't worry about the speed of a program until you actually need to worry about the speed of the program. And so once you have a program that's correct, you want to go back and make sure it's as efficient as possible. So what is the expected performance of the in operator? Here's a small little function down below that just checks to see if a collection contains a target value. Now, normally you're not worrying about performance, but in algorithms, that's my prime concern. And what we oftentimes do is do a quick analysis. What's the best time? What's the worst time? What's the average time it would take to perform that calculation? Well, clearly the best case is when the first element in the list is in fact the one you're looking for. However, the worst case is you have to check every one because the element you're looking for might not even be in the list. Now, if the element is in the list, on average, you could say you have to check about half of them. And so this is normally what you would do. This is a standard naive solution for a common problem. Now, the good news is you can do better, but you have to do some setup first. And that's where we start today. Now, the reason why the contains functionality is important is it's fundamental to so many data structures and algorithms. And in addition, if you're maintaining a collection in some kind of sorted arrangement, you want to check to see if the element is in the collection first. And if it's not, you want to insert it at a very certain location. So not only am I really concerned about whether the value is in the collection, I want to know where to put that value in the collection if it's not already there. And here is a small sample fragment from Python again. You might write this to check to see if a value is not in the collection. And if it's not in the collection, well, then I'll just append it to the end. This is a kind of collection which is unsorted. In mathematics, we would call this a bag. It's just a collection. And without any extra structure, I'm just faced with the normal behavior you would have. Now, when you're dealing with small collections, 1,000 or 2,000 elements, it's really not much of a big deal, but when you get to much larger ones, you really need to pay attention. And so the fundamental problem we have has been dealt with in many disciplines. Consider a phone book, although I don't think they print them anymore, but if you have a phone book, the way that it's sorted is by last name and first name within that. And with this arrangement, it's very easy to find a phone number for a given person, even if it's the telephone book for Manhattan. However, if you wanted to locate a particular phone number in a phone book, well, that would be very hard. You'd have no choice but to start at the beginning and work your way all the way through. But after all, that's exactly what the in statement does in Python. It starts at the beginning and goes all the way. So we already have some insights here that suggest that there must be something better that we could do, but only if we organize the list in some way. And the very simple observation is, if you had a phone book with 400 pages, and then you had another phone book with only 200 pages, well, it's not twice as hard to search through a phone book of 400 pages. As you know, you just have to start in the middle of that phone book, and now you suddenly have a 200-page phone book. So that observation about being able to cut a problem size in half is the fundamental basis for the binary array search algorithm that I'm now going to present. When we present algorithms, it's useful to provide a spec sheet that quickly clarifies the nature of the algorithm, oftentimes provides a small little visual to explain some key part, and then when possible, I either show the whole code or I show what's called pseudocode, which is a high-level representation of the algorithm, using steps and statements and while loops that you're familiar with, but are not specifically a specific language, but in one that you could easily convert to Python or C or Java. So let's start with this description of binary array search. And let's assume that the array in which I'm looking for an item is already sorted. This is what I mentioned earlier about the representation. if you can structure the array so that it's sorted, then that should make it a lot faster for you to do the search. Now, you're still not going one element at a time. That defaults back to the earlier behavior. There's another way of doing it. And the way that binary array search works is that it cuts the problem size in half every step. So instead of looking through the phone book one name at a time and only making one step progress in a massive phone book, you would start in the middle and check to see, is my name to the left or to the right? And then you cut the phone book in half again, and now you're at a quarter of the original size. As long as you divide the problem into sub-problems that are more or less half the size, you're making tremendous progress and are exhibiting what we call order log n behavior. And it's called that because the number of steps that you would actually need to find the element in the list is not based on the total number of elements in the list, but rather on the logarithm of the total number of elements. And the logarithm is the mathematical term that just describes, in this case, in base 2, if I raise 2 to some power, will I reach the final number of elements in the list? So if I have 1,000 elements in the list, instead of searching one at a time, I might only need to do 13 searches because 2 to the 13th power is about 1,024. In this pseudocode description of the algorithm called search, I'm giving it an array, which I assume is sorted, and a target value t. Now, an array is a contiguous block of memory and is usually indexed from 0 all the way up to n minus 1, where n is the number of elements in the list. I'm going to call those concepts the low and the high. And as long as low is less than or equal to high, I have not yet found my target, but I assume that it's somewhere between those two, inclusive on both ends. And so what I do is I compute the midpoint, which is exactly the low plus the high divided by 2. And using integer arithmetic, I know that that will be an integer. If I manage to have found the target that I'm looking for, great. Then I leave and I know that it's there. And in the pseudocode, that's what you see here when I say if t is equal to a mid, which is the element at location mid in the array. However, I might not have gotten correctly the right one, but at least I've got one new piece of information that determines to me, do I look on the left or do I look on the right? If I'm going to look on the left, that means that the target that I'm looking for is less than that midpoint value. And this less than means different things depending on the type. If I'm looking for numbers, well, then it's just smaller. If I'm looking for strings, then this would be a lexicographical ordering, like in a dictionary, where you look for words from A to Z. So if I know that my target value is to the left of the midpoint, then I can safely take my high index and move it all the way down to one less than the midpoint. And now I repeat the while loop and say, okay, continue looking, but now I'm only looking in this half of the collection. And the final else covers the third remaining case, where you're looking for a target value and it's greater than the midpoint. And in that case, I take the low index and I move it up to one higher than the mid. And then this will repeat. And naturally, whenever you see a while loop, you have to ask yourself, how do I know that it's not going to run forever? Well, as long as the low and the high represent an actual range of elements, then you know you haven't yet found your target. But either if high falls below low, or naturally if low gets higher than high, I know that I'm done. And then I just return false because I know that it's not in the collection. On the right-hand side, I have a small little graphic that shows this. And you can see with the small 7-element collection, I'm looking for the value 11. And the midpoint is 9. So I can immediately discount all the elements to the left and focus instead on the right-hand side, which is the subarray 11, 15, and 17. In the second pass, I look at the middle point now, and that's the number 15 as highlighted there. And I know that 15 is greater than my target, so now I can focus on the left part. And finally, in the third and final pass, I found 11 at its proper location. And it's no coincidence that 2 raised to the power of 3 is 8, because this is a size 7 in the collection, one smaller than that. So that's your approximate value for how many times it's going to take you to probe the collection to find a particular value. And if you don't find it, then you know that it's not in the collection at all, because you assume the entire collection is sorted. So now let's go to the code to see how binary array search is implemented. Now that we are ready to start coding, I'm going to briefly describe the environment I'm using. This is the standard idle editor that comes with the Python installation. I'll be using Python 2.7 throughout because I want to make sure that the code that you work on is compatible with older versions as well as the newer 3 series. And I'll be sure to only use functions and capabilities that are available in all Python installations. So let's start. As I've mentioned in the binary array search, there's a need in Python to determine whether a target is contained in a collection. And this is the contains method that I showed on the slides. When trying to evaluate the performance of code, you have to write some scaffolding or drivers to evaluate as they run. Here, I'm doing a very simple example that starts with a number of trials, and every time through the loop, it will double the size of the collection which is being sorted. For now, I'm starting with a collection which is nothing more than the range of integers from 0 up until n-1, so I know that it is sorted. I'm going to use the time module, which comes with Python, to take a snapshot of the clock time. And this is a reasonably accurate way to evaluate the performance of this one function called contains. And briefly, every time through the while loop, it will construct a collection which is sorted, take the time, and then evaluate, does that collection contain the value -1? And then take another snapshot of the time and then print out the difference. What you'll notice is that this value -1 cannot be in the collection because that's a sorted collection from 0 up until n-1. So this guarantees the worst case performance of the algorithm. And that's usually what you are concerned about, just to make sure you understand the full performance. After worst case, we then like to think about the average case, which is, well, just give me a random number. What's the average performance of that? So let's run this, and we'll see what we get. And the first thing that you should notice is that as the problem size doubles, the performance time doubles. And this is the kind of behavior that is something we want to try to break. There's nothing wrong with it, it's just that I don't want to search my phone book through every entry. I want to find a way to more rapidly identify the values that I'm looking for. And so to do this, we now need to implement binary search. So we'll do that now. And I prefer writing code from scratch because it shows how to construct these functions. I've always felt that when you see code in a textbook or in someone else's code library, it's always hard to know, well, how do they start and how do they continue? And so we'll define that function here, which is called bsContains for binary search contains. And I want to check to see whether that collection has a target. I'm going to remind myself that this is an ordered collection, because after all, binary array search will only work if the collection is indeed ordered. Make my quick little comment. Use a binary array search to locate target. Well, it's not locating yet. Determine if target is in collection. As you recall from the binary array search, I want to start by focusing on the low and the high index values. And we start with low and high as follows, from 0 up until the length of the collection -1. And as long as the low is less than or equal to the high, I have something to do. And when I'm done, I would say, nope, it's not contained in the lists. So what was the key part of the binary array search? The key step was to locate the midpoint, which is halfway between the low and the high. And then I checked if the target is equal to that ordered location, then I know that I'm done, and I can return true. But it might be possible that the target value that I'm looking for is actually smaller than that location, in which case I need to look on the left-hand side. And to do that, I take the high value and move it down to one smaller than the midpoint. And finally, the last step, what if it's on the right-hand side? then my low has been bumped up to be mid plus 1. Now the only thing I'm going to change is modify this performance loop to now show me the performance of BS contains for binary search. Now, the first thing you can see is how much dramatically improved the performance is. At the highest level, it's gone from 1200 milliseconds to this, 0.05. That's at least 5 orders of magnitude. And that's the true nature of a log-n behavior, when you can break that linear relationship between the size of the problem and the performance time it takes to solve that problem. The other thing you might note is that these numbers seem to be not constant. They are growing, but they're growing at a very slow rate. And after all, that's exactly what the log function demonstrates. It's a very slow growing function, and it shows you that as you double the problem size, you really only need to take one additional step. And so this is my first implementation of binary array search, and it satisfies the problem as stated. Now that you've seen the implementation of binary array search, you can see how amazingly efficient it is. And so it's naturally a go-to implementation when you're trying to search through a collection. But there are certain considerations we have to take into account. And so let's summarize binary array search. The first thing is it uses a contiguous array, or a list, to store all of its values. As long as your list is small enough to fit in memory, it's really not much of a big deal. But at the same time, it is a significant memory overhead when you get to much larger collections. And you also want to think about, well, how do I create that collection in the first place? If it's provided for you all at once, there's nothing wrong with it. But what if you were building it up one element at a time? Well, then with an array, it's very challenging to work with large blocks of memory. When you have to insert one element, you have to move so many more just to make room for it. Also, think about what the array is meant for. If you want to store a block of memory as a contiguous block, maybe the idea is you want to visit all the elements in sorted order, and that makes it very convenient. If you might find the need to deal with arrays that don't change, that's perfect. And so when considering whether to use the binary array search, take into account the size of the collection. Does the array change or does it not change? And then when you look at your own code in spots where you actually have collections that you're searching for target values, you could ask yourself, maybe I could replace that with a binary array search, which would be very useful. Now, when I have this binary array search that helps me determine whether an element is in the collection, it's actually just half of the problem that most of us face. As I mentioned earlier, I want to check to see if a target value is in the collection. And if it's not, then I want to insert it into the collection. So now I have to change the problem slightly. It's not just a matter of looking for it, it's looking for where the target element actually exists in the collection. So I have to go back to my code, and I'm going to make a small change that will allow me to introduce new functionality to grow the collection with new elements, always making sure that they're properly inserted at the right location. Let's go look at the code. What I want to do is add the new capability called insert in place, which takes that collection and properly inserts the value into the right location. So once again, let me start with the idea that this is an ordered collection. And when it's done, the collection will still be ordered, but target is now inserted at its right location. For this functionality, I can't use the in statement from Python. That will only tell me if it's in the collection or not. I need something that will go through and find where it's actually located. And if you were to do this in a straight Python implementation, you might say, well, let me check each index location in the ordered collection and determine, is that the location where target should go? So if it turns out that the target value that I'm trying to insert is smaller than the value that's currently at that location, and I'm searching through the collection from left to right, I now know that I found the right location for that target element. So I can just insert it at collection, ordered, insert at that target location, and I'm done. However, it might be the case that the target value that I'm trying to insert is greater than all the other elements in the collection, in which case I just need to append it at the very end. This is a naive implementation that doesn't take advantage of any of the structure of the collection. And so once again, I can time the performance of insert in place, and the value that I'm going to insert will be a very large value. It's always going to be one greater than all the other elements. So this way, I can at least get the worst case performance of this algorithm. So now let's run this one. And as you can see, one more time, I'm stuck with this notion that says as the problem size doubles, it starts doubling the time that it takes to insert in place that particular value. Clearly, I have to find some way to take advantage of the binary search capabilities, but how do I do that? The good news is that there's a small change you can make to the binary search implementation that will allow it to be used, and both for the containment as well as for knowing where to insert a new element. And let's start with looking at the implementation itself. When you find the target value in the collection, that is where presumably a new value would be inserted if it happened to be the same as one that was already in the collection. So instead of just returning true, I'm going to return mid, which is in fact the index location of that element. So I'm no longer going to say, does it determine if the target is in the collection? I'm going to have it return index position of target in collection. And what's nice about that is that if I return a negative number, that's a sign that it doesn't exist in the collection. And if I return a positive or non-negative number, that tells me where target is in the collection. And I can do a small, elegant trick to tell where target should be inserted in the collection if it's not already there. As you recall, binary array search will use low and high index values to narrow down the search space in the collection where that target element must be. And when it gets to the very end of this while loop, it has exhausted all of its capabilities. But the good news is that the index value low tells you where target would have been if it had ever existed in the list. And I can't just return low because after all that's a positive number, and so the calling function would have no way to discriminate between containment where it's actually there and when it's not actually in the list. So there's a really useful trick that you can do is you return a negative number, but not just any negative number. I return a negative number which is in fact what that low index value is plus 1. And with this small little change, what I'm able to do is modify insert in place to first find where that element is in the collection. And I call BS contains to find where target would be in the collection. If it turns out that IDX is a negative number, then I now know that target is in fact not in the collection, and I've got the value of where I can actually insert it. So let's look at that. If IDX is less than 0, then I now know exactly where to insert the target element. Indeed, where is it going to be? It's at that ordered location. I can insert it. I can't just say IDX. Remember, this is the negative value of low plus 1. So what I do is I just say, well, let me negate that. And that's where I want to put target. And if it turns out that the ordered value IDX tells me where it is in the list, then fine. Now I can insert at that location the target. So I've taken what was a linear exploration through the sorted collection, and I've turned it into a first do a binary search to see if target is in fact in there, and in fact where it would be if it's not. If IDX is ever negative, it means that it's not in the collection to begin with, and so I know exactly where to insert it. If IDX is non-negative, well, then I know this is where it would be inserted. So let's start with the performance again. You'll see that the performance is much better than it was just a moment ago. However, it's not as blindingly fast as the binary array search containment was, and that's strictly a matter of Python. When you're inserting a value, you have to deal with very large arrays, and moving those around in memory takes up a significant amount of time. But at least here, you see the performance benefit is once again 4 orders of magnitude. It's a dramatic speed-up increase, and it now completes this concept of containment. When you have a collection, sometimes you want to just check to see if an element is in the collection, but in other times, you're trying to maintain and update the collection itself. And so using this capability, you can now truly have a binary array search that allows you to work with static arrays that don't change over time, or arrays that you are yourself growing over time.